Anna. Okay, today is May 31st, and we're going to be continuing with the study of review. Basic concepts on hydrodynamics, and especially we are interested in reviewing basic concepts on its ideal fluids. Okay, and the motion of these ideal fluids, we call them potential flows. See, every time you listen or you read potential flows, that means that or irrotational flow is basically equivalent. That means that the viscosity is not involved, it's not considered. So basically that allows us to calculate part of the forces. And the other part, which depends on the viscosity, usually what we do is we rely on experiments, okay? Up to now, in nowadays, there is a lot of effort in trying to obtain this information using simulations. But so far, this is the procedure that we're going to be using, okay? So let's continue. Today, we're going to deduce Laplace's equation for irrotational flow, and then we're going to deduce Bernoulli's equation. That's a topic, that's an equation that you have used since you were in high school. But our deduction will include a new term, and this new term allows us to apply this equation for cases where we have time dependence. Of course, if you move up and then you move down, the velocity changes in direction. So if you go back to your high school class notes, there was no time dependence. In the deduction that we're going to be presenting this afternoon, there will be time dependence. And that, in the next session, will allow us to calculate added mass, because added mass is a concept that we can calculate when we consider dependency of time of the velocity. That means if you talk about that the velocity depends on time, that means that you have accelerations. Okay, so that's the agenda for today. At the end, I don't know if there will be some time in order to mention, just to mention about the homework that I just posted, okay? So let's go to that. Can you see my full screen, Giovanna?
Yes.
Okay. So first, we are going to work with cases where we have no influence of viscosity, okay? Now, if you have a sink, okay, if we observe a flow in a sink, okay, in the kitchen of our house, okay, we have something like this. That's a big sink. And at the bottom, we have a hole. Okay, so this is water. And because the water is flowing through here, through this hole, okay, some motion is developed in the sink, okay? There's some rotative motion. Now, if you pay attention, okay, to regions close to the edges of the sink, okay, you can put something like this. It's like a floating cross, right? And this floating cross start moving because the whole portion of water is moving. And the thing is that this cross, you see, there's originally is in this element is in this direction, but here it start rotating. Okay, so this element here is now in this position. That means that there is some rotation, and that's something similar to any other floating object in this region. See, this element is like this, and now it's like this as they move. So this is some rotation. Similarly, when you put some of these floating objects close to the hole of the sink, and here in this area is quite noticeable, right? There is a lot of rotation. Okay, so it's rotating as they move in this direction, and finally goes inside. Okay, but now what happens in this area here? Okay, in this area, let me change color. What happens is that you put one of these objects, right, like this one here, and as they move, they keep without rotation, mostly. So it's like saying in this area, okay, there is no rotation, see? So we can say that it's an observation. In this area or region, there is no rotation. Okay? After this observation, okay, some researchers concluded that if we consider that we are in this area where no rotation is acting or is being produced, that means in this area the shear effects because of the viscosity are neglectable. Okay, so let me see, what is my pointer? Here is my pointer. Which is related to shear. So in this area, the effects of viscosity are neglected. And this area is called irrotational flow. Okay, so it's just an observation, right? And we said, okay, in this area where we have no viscosity effects because there is no shear, we can say that there is no rotation. Okay, and that no rotation, we are going to be evaluating, okay, evaluating through a concept, and that concept will be the circulation. Okay, so when we have no rotation, we can say that there is no circulation. That's what it's coming. Okay, so that means that in general, okay, if we are away from these regions where you have a lot of shear influence, okay, that's viscosity influence, okay, we can assume that the flow is irrotational. That means that in this region, the viscosity is not important. And in these regions, as I'm going to explain in the next slide, that means that the circulation is null, is zero, okay? So this is the definition of the circulation, okay? As you can see, it is a scalar, so we have to be careful, okay? So this is dot point. This is dot product. Okay, so this dr is a vector, and this is the velocity vector. And the product of those two is, the result is an scalar. Okay, that's why this gamma is the circulation is an scalar. Okay, so in the case of regions where we have neglected these rotational effects, we can say that the integration of the circulation in a closed path is going to be 0. Okay, so let's explain what this means. Okay, so this is a closed path. Okay, so if we take one little piece, a differential element of the path, okay, we can set up a differential vector, align it or tangent to the surface. So dr is a vector which is tangent to the path. Okay, and you see that it is basically, I draw it tangent. Okay, so the length is the amplitude of this vector, and the direction is tangent to the path. So that's this vector. And the other is, of course, the velocity. Okay, so if we assume that a flow is irrotational, okay, that means that we complete this closed path integration, and the result is going to be 0. Okay, so we said that for a closed trajectory, okay, for a closed trajectory, the circulation is 0 for irrotational flow. Now, this is a good assumption, and we will show that why. Okay, so if we integrate in the closed trajectory, for example, we go from A, B, C through D and close to A, right? So this is A, B, C, D, and A. We go all the way. We can say that this is equal to the integration from A to C, okay? So A, B, C, and then we complete the closed path by the second part, so from C through D until A, back again. So it's going to be C, D, A. And we are saying that this is equal to 0. Okay? Now, we can say then that the integration from A, B, C is equal to minus the integration from C, D, A. And you recall from the calculus of several variables that this is equal to minus if we go in the other direction. So with this minus, it's going to be positive, the integration of A, B, C. So we are saying is that the integration of this, the circulation, from A to C, from here, until here, is equal to the integration from A through C, but with a different path. That means that the path is different. The only points which coincide are the first and the end. So that means that the integration only depends on the end points. Okay? Now, if that is the case, okay, that is the case, then we can say that the integrand has to be a exact differential. Okay? This is only possible if the integrand is an exact differential. Okay, for example, you say the integrand, okay, is equal to an exact differential. What's the integral of this? This is equal to phi, okay, from A to C. So this is equal to phi of C minus phi of A. You see, in this case, okay, you only worry about the end and the starting point. You don't depend on the path. So in order to have this being this equal only to the difference between the end values, then the integrand has to be equal to an exact differential. So what we're going to be doing is equaling this integrand, this is a dot product, to an exact differential of another function that we're going to call it phi. And through that, let's see what is the conclusion, okay? So this is the integrand, and we're assuming that there is no circulation. So this is going to be equal to 0, okay? So the integrand is going to be dr dot velocity, and then we are saying that it has to be equal to an exact differential. Okay, now, this dr is dx in the I direction, in the x direction, dy in the j direction, and dz in the k direction, okay? And this is dot product with the velocity. The velocity has three components, ui plus vj plus wk. Okay, so we're gonna get the dot product of that. And the differential of phi, this function, is going to be the derivative of phi with respect to x dx plus the change y plus the change in z. Okay, now this dot product, okay, so it's going to be equal to u dx, so this is u dx, plus v dy, because the other are orthogonal, plus w dz. And this is equal to that. Okay, since this is differential in x, in y, and z, the only conclusion is that u has to be equal to d phi dx, v has to be equal to d phi dy, and w has to be equal to d phi dz. Okay? Or in a very compact way, we can put that the velocity is simply the gradient of phi. Okay? Now, phi is what we call the velocity potential. Okay? So instead of trying to find u, v, w, we're going to try to find phi. Okay? And phi, the gradient of phi, will be equal to the velocity. People, is there any questions so far? Any question so far, people? No? No question? Okay, I'm going to have a question for you. Mr. Manrique, what are the units of phi? Something that we always have to worry about, units. What are the units of phi?
I'm not sure. I think it's What's the meaning on?
No?
No, no.
Mr. Matute, what are the units of phi? Please, everybody, turn on your cameras.
Okay.
Come on, I need to know you.
It's the velocity in
Mr. Matute,
yes.
units of phi, come on. Here,
Okay.
from here. Mr. Jimenez, what are the units of phi?
Square over time.
Length squared over time, yes. How did you do it?
就是 see the derivation.
Exactly. I mean, you have length squared over time. Okay. So when you differentiate this, you put an extra L in the denominator, and the result has to be L over time, because that's the result has to be velocity. Okay. So from now on, meters squared per second, those are units of velocity potential. Okay. We have to be careful with that. Now, the title of this subchapter says that we're going to deduce Laplace's equation. Okay. Now, so this will replace the velocity, but please have in mind that this is specifically for cases where we have no circulation, right? And that's a characteristic of what we call irrotational flows, only irrotational flow. Okay, now, remember in the previous class, we deduced an equation for the conservation of mass, specifically for liquids, where we have no changes in density. Okay, so let's combine these two equations. Okay, so if we consider fluids with rho a constant, okay, in that case, we said that the continuity says this: divergence of the velocity is equal to 0. That's conservation of mass. Okay, now what we're going to do is we have conservation of mass. If we have a fluid, no matter if it is viscous or not, that equation has to be satisfied if the density is constant. But now we are going to combine specifically for the case when we have no viscosity. So what we do is we take this equation and replace it into here, and we can finding them. We have nabla dot nabla phi. It has to be equal to 0. And this is nabla dot phi is equal to 0. And this is Laplace's equation. It's a second order differential equation, so we need to specify one boundary condition in every point along the boundaries. Okay, if you replace this, then this is equal to the second derivative partial of x plus the second derivative partial of y plus the second derivative partial of in z has to be equal to 0. So this is exactly equivalent to that. Okay, so this is a second order linear constant coefficient partial differential equation. So as I said before, you need one boundary condition in every point of the boundary. Okay? Now, you immediately think, oh man, that's going to be difficult. Yeah, but remember that usually we work with 2D problems. Okay, so that brings a lot of simplification. So we're going to get only the first two terms. Okay, and that's usually what people have done in this area. Okay, instead of dealing with 3D problems, okay, they try to move to 2D problems and then integrate it longitudinal. So that's a big relief for everybody. Okay, so if you see that somebody is working with Laplace's equation, that means two things. First, that they're working usually with liquids, water. Why? Because the density has been held as a constant. And second, they are saying to you that they are neglecting viscosity, so that they're working only with irrotational flows. Even though they don't tell it to you, okay? You have to remember this. Okay, so Laplace's equation, it's conservation of mass with fluids with constant density and also no viscosity. Okay, no viscosity comes through the assumption that the flow is irrotational, and so the circulation is null. Okay, we're going to be doing an example in a couple of minutes about this. Okay, so that's Laplace's equation. So every time you see in this area, you see that the equation that you have to solve is this, Laplace's equation. After you find phi, then you can calculate the velocity with the gradient. And with the velocity and the next one, which is Bernoulli's, we're going to be able to calculate the pressure. Once you have the pressure on a body, you can integrate it and calculate forces. Okay, and the forces, of course, acting on a body means possibility of dynamics, which is what we need to study here. Okay, so now let's go to deduce Bernoulli's equation. So for this deduction, okay, this is Euler's equation. You have to review this for the homework. I just want you to review. That's all. Okay, and I'm going to say a couple of words about this. Okay, so in this case, on the right-hand side, these are the forces. And this is proportional to, oh no, this is acceleration, I'm sorry. Please don't make any scratches on my because I can get confused with this, people. Be careful. Okay, this is acceleration. And you see here, you have the denominator, you have the density. Okay, so this is divided by the density. Okay, if I make this, I multiply the whole thing by a differential of volume. Okay, this differential of volume on the left-hand side, and I put the density on the left, I will have a differential of mass. And you will see that, okay, this is the forces equal mass times acceleration of a differential element. So that's basically, that's what you're doing. Okay, now here, you see that you have the pressure and you have the gravitational acceleration. So in the forces, you have two forces, surface forces and body forces. And this concept probably you remember from fluid mechanics. So in the case of the surface forces, we only have pressure. Okay, there is no viscosity. So please remember this, okay? In this equation, no viscosity. So we are consistent, okay? Laplace means no viscosity, irrotational. Here, Bernoulli's either, there is no viscosity applied. Okay, so to apply this action, pressure, you need contact, surface to surface. And for the body, you don't need contact. Remember, okay, from the center of the earth, you are being attracted in this direction. And that's the origin of this force. You don't need contact. Okay, so, and the only force, body force that we're going to be considering is the gravitational attraction. That's the only force that we're going to be considering. Okay, so pressure, gravitational attraction. And you see that the gravitational attraction works in the third degree of, in the third direction. So we have, so this is X, and we call it direction 1. This is Y, we call it direction 2, and this is Z, and we call it direction 3. Okay, don't worry, in general, we're going to be working with 2D problems, okay? If you don't behave, yes, I will give you a 3D problem. But since you are very good students, we're gonna keep working only in 2D, okay? That's that. Now, here, for example, you have like a little element, differential element. And let's suppose I have a pressure here. And let's suppose on this side, this is the volume. On this other side, I have P plus dP. You see that there is a differential. That means that in general, okay, the pressure has changed in going from this side to this other side of this element. Okay, now you see that there is some cancellation. See, this points to the left, this points to the right. And this is the net surface force on this body. But you see, if this is positive, that points to the left. And that's why you see here this negative sign. So if dP dx is positive, that means that this dP is positive, and that gives us a net forces pointing to the left. And that produces a forces which tries to decelerate this term. Okay, it's like having a net force pointing to the left. So you are going to suffer a negative acceleration. Okay, that's the reason why you have it here. You can reason similarly for the other term, for the body surface, but I'm not going to do it. I'll let you do it. Okay, now on the left side, okay, this is something which is very important. You see, there is a derivative with respect to the time. And there is also this term here, okay? And the two compose what we call the total derivative, okay? So when you see this d over dt, okay, this is what we call the total derivative. Some people call it all different ways, but that's the idea. That means that you consider in a certain point, you could have the rate of change in that point. Okay, for example, you have this point of control and particles pass by. And when a particle passes here, I check the velocity. And the next particle increases the velocity. That means that the velocity in this point is changing in time. So that there's a change of velocity in time, that means acceleration, right? But not only that, okay? But if you see a particle which is passing right now here, okay? But this particle moves, okay? Moves to the right. And as it changes in position, it can also change in velocity. Okay, so that's another way that you can see that there is a change in velocity. See, you change the velocity as you change in position. And that's the second term. Okay, and the second term is V dot nabla. And this term here is equal to U d at dx plus V d dy and W d at dz. If you apply the two components. See that these are two vectors, right? This nabla, remember, is the partial with respect to x in I direction plus partial with respect to y in y direction plus partial with respect to z in z direction times k. So when you do this product, that's what it means. That means that you check, see, as you move in the x direction, how much the velocity changes in this direction. That's an acceleration. Okay, and if you analyze fluids, of course, you have to consider both components. Okay, so as you pass by one point, that's the first term. But as you move, you pass at a very instant, you are here, but you're going to change in position. So you have to consider that also as a possibility of acceleration. And that's what we call the total derivative in many cases. Okay. Now, another thing which is very interesting in fluids is that they usually apply what they call the repeated subindex notation. Okay. So what does that mean? That if you have in a term, one of the indices repeats, okay, that doesn't indicate that is one single term. That indicates that you have to consider as a summation all the possibilities for that index. For example, in this case, in this term, okay, this term here is the one that we have up here. Okay, so in this term, you see that the J, let me change, you see here, you have J is repeated here. So when you see this term and they are using repeated subindex notation, they don't mean one single term. That means that they're going to add, and for this subindex, they're going to include all the possibilities. Okay, so in general, we're working in three directions, right? So J could value 1, 2, or 3. Okay, so if J values 1, this is U1 and this is X1. Plus J values can value 2. So this is going to be U2 and this is going to be X2. So U2, that's the velocity in the Y direction, and we call it V. And X2 is what we said here. Instead of putting X2, we said is Y. And similarly for the third term. Okay, so that's something which is very common in hydrodynamics. Okay, remember, I am not a hydrodynamicist. Okay, who is hydrodynamicist in our department? Who is the hydrodynamicist in our department? Who is the hydrodynamicist in our department? Ms. Freire, who is the hydrodynamicist in our department, in our program? And you see, it's a little bit, that's what we call them. Hydrodynamicists are a little bit. Can't you imagine? Think about this type of things. Yeah, that's typical of hydrodynamicists. People from structures were more. Okay, I'm joking. But yeah, that's a lot of mathematics and we have to go through this. Okay, so that's typical of these equations. Otherwise, they will be very long, very long. Okay, so let's start with this equation. Summation of forces equal to mass times acceleration for a particle, fluid particle. And let's, from there, we're going to deduce the linearize. Well, first we deduce Bernoulli's equation, and then we linearize it because that's usually the way we use it. Okay, so let's go. So that's the equation. It's the same equation that we had before. Okay. Since we are saying that this is irrotational, that means that we are considering no viscosity. Okay, so we said that the velocity is equal to the gradient of velocity potential. What are the units of the velocity potential, Mr. Matute? Oh, you know it, right? What are the units?
L squared over time.
Yes. You see, you learn it. Good. Okay, now, so we replace this in here. Okay. So that's there. So we said the derivative of time with respect to time of the velocity, but instead of the velocity, I put this. Uj, so that's Uj. I have Ui, that's Ui. And on the right-hand side, we have the forces, the two forces, surface and body force, acting on the differential element. Okay, you have to reduce this equation so you can know where it comes from. Now, let's go on with this. Now, if phi is good enough, this is something that you learn in calculus several variables. You can switch the order of differentiation. Okay, so here, first you differentiate with respect to xi, and then you differentiate that with respect to time. So first this, and then with respect to time. But if phi is a nice function, we can switch. And first we differentiate with respect to time, and then with respect to x. Now, similarly for this case, okay? So this is the second derivative of phi mixed and multiplied by the phi dxj. And you can prove that this is correct. So if you differentiate this with respect to xi of this is equal to twice. So that cancels with this 1/2. And then twice d phi dxj. And then you have to differentiate this with respect to xi. Then you get exactly the same thing. So instead of writing like this, we write it like this. And finally, this is the way we're going to write. And you can see that this term here has the derivative with respect to x outside, the derivative with respect to x outside, and this has already the same way. So the three terms in the equation can be written in a compact way like this. So remember that I values 1, 2, or 3. We have three directions, okay? So I is 1, 2, or 3. The derivative with respect to x or respect to y or respect to z of all of this is equal to 0. What can you say about this? Anybody? What can you say if the derivative of that with respect to x, with respect to y, or with respect to z is equal to 0? What can you say about this term in parentheses? What can you say? Buddy?
It is constant.
It's a constant, or It doesn't depend on X, on Y, on a Z. But we have another variable. The another variable is the time. So this term inside the brackets does not depend on X, on Y, and Z. That's the only way, if you differentiate with respect to either one of these three variables, the result is 0. So that means that in general, that's going to be equal to a constant, okay? Which can depend on time, okay? And here you can recognize that this is velocity squared, okay? And this is the way usually you write it when you were in high school. So this is the velocity This is the way you write it in high school. Okay, this is high school. The pressure, you have rho gz, and you have 1/2 of the velocity squared. But now you have this term. Okay, and this is what we were interested in, since our problems will be doing something like this. When you go up, you have velocity, positive velocity. And you go down, the velocity has changed from positive to negative. So there has to be a time dependence. And that's what we're looking for. We were looking for in this deduction. Okay, that term makes a big difference. You will see that in a minute. Okay, any problems so far? It's 4:57. We're going to take a break here. And when we return, we're going to make a review of an example. It's a classical example. Please, the example that we're going to present here in this session is going to be a steady case. So that term will not appear in this example. But in the next subchapter, you will see that's the main the most important part in the next subchapter. But in the example that we're going to be doing in a few minutes, we're going to consider a steady case. You have to be alert, because according to the characteristics of the example that you want to solve, you can neglect, you can discard certain terms. Okay, so let's take a break, 5-minute break. You can stop the recording, Miss Giovanna. 5-minute break.